All right, we're back. Okay, so before we were so rudely interrupted, what were we saying?
It takes a long time to access memory.
I know, yeah. That's why it took me 5 minutes to start up. It's a long time to access memory. Okay, so we were kind of saying, okay, we can kind of load the address that we want to read into memory on the first cycle, right? And then that memory is not going to come back to us, right? We'll send out the request. We'll say, hey, read the address that's in the MAR, and we'll send that command out to memory. And that'll take some time. It's not going to come back immediately like we had originally said, right? If we put a data out on the register onto the bus, we said, hey, we can latch that back in on the same cycle. All right, and that's basically what we're doing here. We latch it out on the falling edge, and we latch it in on the rising edge, which is at the very end of that same clock cycle. Okay, so with memory, what we're saying is in the very least, it's going to take one cycle, right? And this will help us to conceptualize something that will get more complex later, but just keep it simple now. So let me zoom in a little bit here. Okay. Okay, so essentially, you can see we have 2 clock cycles, right? If you look at the little lines up here, clock cycle 1, clock cycle 2. So essentially what it was saying was, hey, this first one, you know, we load the MAR and all that stuff, and we send out that command, okay? And what it said was, for now, we're going to assume that that MDR is going to be loaded, meaning the value is going to come back from memory into that register, which is when we have access to it, right? So remember, this processor can only work on stuff that's in the registers. And what we even saw, right, was even more so, the processor can only work on stuff that's in these few registers that we have to work with, okay, at least with this microarchitecture. Okay, so if we want something from memory, we can't just compute on it directly. We have to bring it back into one of the registers. Then the ALU can do some kind of computation. Okay, so we're saying here, the memory read and return it back into that MDR, depending on what we're reading, at the rising edge of the second cycle. Okay, so where is that? Well, right, remember we made the request here. We're saying at the rising edge of the second cycle, okay, which would be basically right here. It's the rising edge of the second cycle. So we've got this whole cycle where what are we doing? Nothing, right? At this point, we just kind of killed a cycle because, hey, it just takes that long to read something from memory. And like I said, in reality, it's going to take longer than a cycle, but we'll just start there for now because we're starting to see, hey, there's basically like this stall, like our processor is still cranking, but it's stalled in its practical execution of work. All right, so what we'll see is we can do other operations while waiting for memory, okay? And these must not depend on the memory being read immediately. So we'll get into this later on when we start talking about concepts like pipelining, and we'll start talking about concepts like hazards. So yeah. Sorry, I don't know, it makes me laugh when I say the word hazard. It reminds me of grad school. We had this professor who he would always say haja. The whole semester he would say, and then you have a haja in your circuit. And we didn't know what he was talking about for like weeks. I don't know, maybe we should have read the book or something, you know? We're just like, what word is he saying? Like, and eventually we finally all figured out he was saying hazard. This is like an advanced architecture book. So it's just kind of, sorry, if you catch me like smiling, that's probably why I'm like going back to my grad school classes. So I would try to pronounce those words clearly for you, hazard. All right, he would also do this. You have to capture the data. And he would always do this when he would talk about the data coming into the reg. Capture the data. So I might start doing that too. Okay, so let's take a look at some of the control signals. We've talked about some of these, all right? But just to talk about them all in one place. Okay, so we have, if we look at this C bus, right, highlighted in blue, we have 9 signals to control writing data from the C bus into the registers. Okay, so if you count all these arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so to latch data back in, there's 9 signals that can basically control which register comes in. There's also 9 signals to enable the registers onto the B bus, right? So if we want to output a register, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What we will do in this particular, I should say, what this microarchitecture decides to do is it will actually add some decoder circuitry to compress these 9 signals into 4 signals, right? So with 4 signals, I can represent how many, right? I can represent 16 unique things, right? I can count to 16 with 4 bits. So that's the idea. We'll see, like, I don't want to have all 9 of these signals in my instruction format. I really only want 4. And we'll see that in a second with instruction format. And then I'll actually show you the circuitry and how it simplifies our instruction. Our instructions to be shorter, but our circuitry will get more complicated when we add this decoder in there. Okay. And then we have 8 signals to control the ALU and the shifter functions. Okay. So the 6 that we saw a few slides back, right? We've got F0 and F1, and then enable B, enable A, invert A, and then carry in. All right, so those are 4 between those 4, and then 2 more items. So those are the 6. A and B are just treated as, you know, they're not control signals. Those are just actual, the data inputs, right? Okay, so those are the 6, and then the shifter has 2 as well, 2 bits. Okay, like for instance, am I shifting to the left? Am I shifting to the right? Okay, and then these last 2 aren't shown, but we have 2 signals to indicate the memory read and write via the MAR. So kind of up here, basically to activate, they would kind of be almost, maybe if we drew them like right beside these, right? Are we going to send out whatever's in the MAR onto this bus? Are we going to send out whatever's in the MDR onto this bus? Okay, and then 1 signal to indicate a memory fetch. Okay, so we're going to send out data onto this particular bus. Okay, so you can imagine maybe that these signals were almost, well, no, I guess it's different buses. So we could probably draw 3 signals right here for those. I'll maybe do that in the slides. Okay, so if you are looking at this on your computer screen, these colors should look a little bit more different than they are. Right now, I'm kind of looking at them, they all kind of look like a blue and a green. Or kind of like muddied versions, but they're more colorful on the slides if you want to look at those on the slides. But nevertheless, this is our instruction. Okay, this is the instruction that we would get, and so essentially this is everything, right? This is what is the ultimate encoding from the assembly instruction. So that move, that add, the 0s and 1s that gets boiled down to, this is basically an example of that. Okay, we looked at this when we were talking about MIPS from the MIPS perspective. So this is the micro instruction, we would call it, for the MIC1. Okay, and the MIC1 is just this first version of the micro architecture for this IJVM that we're looking at. Okay, this thing over here. The rightmost 24 bits map to the 24 control signals on the last slide. Okay, so we had 9 here. We reduced this 9 to 4, so that gets us to 13. Add 8 to that, that gets us to 21. Add 2 to that gets us to 23. Add 1 to that gets us to 24. Okay, so these 24 signals that we just talked about, okay, are coming from this instruction. And we can see that here's the 4 from that B bus. We remember we decoded that or encoded those from 9 to 4 bits. Here's the 3 from the memory, the 2 MAR and MDR, write and read signals, the fetch. Okay. Here is the C bus signals, the blue ones, right? So kind of have it here if you can make out those colors at all. And then the ALU, right? So the 6 bits here, you can see the F0, F1, enable A, B, and so on and so forth. And then down here, the 2, you can see it's a shift left logical and a shift right arithmetic type of bits. Okay. And then we add an additional 12 for basically branching stuff, which we haven't talked about in the last few slides because we've been focused on the ALU so heavily. But obviously, you know, adding and logical ands and stuff is not all we want to do with a processor. Oftentimes we want to do jumps, right, and branches. So we have 9 bits to be able to handle like an offset to the next address, and then a few bits to determine whether we want to jump on certain conditions, like if it's 0, right, a comparison is 0 or something like that. Okay. So this is the breakdown, right? I think we basically just talk through this a little bit. Up here, this is the, so I didn't point this out, but up here, this would be the encoding of that B bus. So remember we had these 9 registers, right? And we said, oh, we're gonna take those 9 registers and we're gonna encode that into 4 bits, okay? So the 4 bits is right here, and this is the encoding, right? If all 4 of these bits are 0, then what that is going to do is it's going to activate just that MDR bus, right? If we just have a 1, it's going to activate the PC. 2, right? 0010, it's going to activate the MBR, for instance, and so on and so forth. Okay, so that's what's going on up there. Okay, so again, I think we've pretty much explained all this stuff, so I won't read it again. Okay, now the ordering of these bits, you know, when we're looking at it, may seem kind of arbitrary. Like, why do we have C before B, and why do we put the memory right there in the middle of C and B? Like, you know, it seems kind of like if I was to just sit down and do this, I would do it maybe alphabetically or organize at least the kind of the buses similar. You know, the B and the C seem to kind of be doing something, but this is all ordered to minimize wire crossings. Okay, so we haven't really gotten that low yet. But in order to minimize the wire crossings is why this particular order was chosen. Okay, so let's actually look at an expanded version. Okay, so this would be an expanded block diagram of what we've been looking at. On the left is the data path, and we've been looking at that, obviously. On the right-hand side, this new kind of chunk and all these extra wires, this is the control circuitry. Okay, so if you recall from that early one, right, we go way back here. Remember I said, hey, that control unit, we just kind of look at it as a box. But what I said, if you remember, is it's not really like a box. It's really like a, almost like, think of it like a spider web of wires and circuits all throughout. Okay, so this is kind of control circuitry. It's all over the place. Okay, so let's take a look at this. And again, this is one thing that will translate better to your computer screen than perhaps a little washed out projector. All right, so here, if we just kind of look at all these wires, we'll start to see, you can see, let's start with the C bus, since that's kind of like the biggest one. We've got these 9 bits from that C bus, and this right here, right, is literally just this, okay? So I've got those 9 C bit bus, those 9 bits from the C bus, you can see they're coming down, right, and connected to each one of those, okay? We can see the B bus. Remember, we use that decoder. So we've got 4 bits. You can see it's labeled here, 4 bits coming into this 4 to 16 decoder. Okay. And out of that decoder, you can see those are, you know, we get those 9 signals. And then obviously the 4 to 16 decoder can do more stuff, right? But we'll end up wasting 7 of those bits because, you know, if we can encode 16 things, but we only need 9, we basically have 7 wires that we could connect to something if we wanted to, but we just don't really have a purpose or a reason to. Okay, so that's the B bus. You can see the ALU, right? The 2 bits coming to the shifter, and then the other 4 bits coming to the ALU. If you remember here, right? It was the top 6 of those bits that were the ALU, and the bottom 2, the left 2 that were the shifter, and that's basically what you see here. Right, so you can start to see, you know, we're avoiding wire crossings. You can go to different layers, but if you start getting into laying down circuits and PCBs, or in this case, it's silicone, anytime you add extra layers, you're adding cost, right? You're adding, I mean, you can think of it, right? You're adding more material. So that's true whether it's PCBs or in silicone. Okay, now they may already have a second layer, which is why you see some things crossing, like you see the buses are crossing over some of these control circuits. But you know, if there's 2 layers, you want to avoid going to 3, 4, or whatnot, because every layer adds a lot of expenses. Actually, the channeling down from one layer to the next is what adds a lot of expenses as well. It's what they're called vias. Okay, so we've looked at the ALU. Okay, here's some jump and address circuitry, which I won't talk a whole lot about. Other than to just point it out. You can see it kind of goes into some other little circuitry that gets connected. You can see the address goes into a number of different places. We won't need to break that down too much at this point. Okay, but those are there. if we want to do those types of instructions. Okay, so now there's one big thing on here that I haven't talked about. Okay, and you can see this says 512 by 36 bits control store for holding the micro program. Okay, what we see over here, okay, and maybe didn't explicitly say it, but if you add up all these bits, if you recall, we said, hey, these far right ones are the 24 bits. We did say that, right? The rightmost 24 bits mapped to the 24 control signals. So that takes care of these. But then we added another 12 to that. So this is a 36-bit, it's called a micro instruction. Okay, so the way that this particular microarchitecture works, and this is a somewhat common design. This is maybe not terribly efficient, but it's flexible. Okay, so it's almost like a combination of hardware and software implemented in the hardware, so to speak. But what we can see here is we have 36 bits. So that should ring a bell to you all of a sudden, because that's how big our micro instruction is. That's, if we want to do a move or an add or something like that, it's 36 bits, right? So you can see here, basically I have 512 different versions of that 36 bit, okay? And these are the different, basically I'm saying, hey, I can have 512 different configurations of control signals that can activate my circuit to do anything at any one time. Okay, and we'll break that down a little bit in just a second. That's still probably a little bit nebulous. Okay, but the control store holds 36-bit micro instructions. Okay, this is not in main memory. Okay, now this IJVM is kind of like this virtualized thing, and it's not really like there's silicon that implements this particular structure because it's simulated, it's emulated, however you want to say that. But if this was a real circuit, then this control store would actually be implemented in silicon. You can imagine if I want to update this, I might need to do like a firmware update, right? Where it's like wiping it out at the electrical level, not necessarily just with high level. I mean, it's all software that's doing it. That's not main memory. It would be in the hardware itself, okay? This doesn't hold ISA instructions, okay? This is holding micro instructions. So I want to be clear there because we haven't really talked about micro instructions. Okay, but micro instructions are not always executed in sequential order like main memory. Each micro instruction specifies its next successor. Okay, none of that's probably going to make too much sense until we actually look at some micro instruction code. So keep that in mind. Don't wrap your mind around what I'm saying too much. This will be one of those slides that in retrospect, like, okay, now that kind of makes sense. Okay, the control store is read-only memory, so it's like a program essentially for how to operate this device. Okay, what you'll see is, if we want to do an add, like what we think of as an ISA or assembly add, there will be a number of micro instructions to execute to carry out that one high level add. And so what we're getting at is this, or one of the original things that we talked about was we started at the beginning, we said, hey, if we do an add, let's just assume it takes one cycle. But I would always say that's not really the case. And we're going to start to see that here when we say, hey, let's do an add. Oh, it's okay. So now I see to do an add, and we already kind of saw that in the early where we said, hey, add two numbers together. Well, we had to send data through this twice. All right, we had to send the PC down and get it into the H register, and then we sent SP down. Okay, and that took us effectively more than just a single cycle to do that. It took us 2 cycles. Okay, so this control store, it's going to have read-only, and we'll end here in just a second. It's going to have read-only memory micro instructions. Okay, it's going to have its own micro program counter, so it knows where it is. And that's going to hold the next micro instruction address to execute. Okay, and then the MIR, the micro instruction register, is going to hold the micro instruction being executed. Okay, so it's the same thing that we've already seen. We've seen the program counter and the IR at the assembly level, or at the ISA level. Now we're going to have one of those for the micro instruction. So this, for every, just imagine it this way, for every assembly instruction, for every ISA instruction, there's going to be maybe 3 or 4 micro instructions needed to basically do the physical cycles of activating activating things, turning them on and off. Okay. So we will end there, and then when we come back on Tuesday, we'll break down these micro instructions a little bit more, and we'll actually look at some microcode. So have a great weekend. I'll see you all on Tuesday.